Okay, now moving on to the next property, rather before moving on to the next property, let us first acquaint ourselves with circular convolution. Now, in circular convolution, before going into that, let us assume two signals if x1 of n, x2 of n are two unique discrete signals with their consecutive with their length be n1 and n2 respectively. So if these two signals are linearly convolved, so when the signals are linearly convolved, then say the convolved result is x3 of n will be equal to x1 of n convoluted to x2 of n. Now these two signals will have a length of n1 plus n2 minus 1. This is true for any form of linear convolution, and you may verify it by taking some arbitrary value of this signal and then linearly convolving it one another. You will see that the length of the convolved signal sequence will be n1 plus n2 minus 1. Now, in our case, if n1 is equal to n2, then as per DFT, the signal x of n1 convolved with x2 of n, I mean x1 of n when convolved with x2 of n cannot exceed the limit from 0 to n minus 1. So we are talking about the DFT convolution. In case of DFT, if we are to linearly convolve these two signals, the length must not exceed by any chance from 0 to n minus 1. But as I have shown before, this is not the case in linear convolution. Of course, whatever may be the value of n1 and n2, this value will always be greater than 0 to n minus 1. Same is the case if n1 is not equal to n2. This value will always be greater than n minus 1. Now, if n1 and n2 are of different length, which one we shall consider as capital N? Now, logic suggests, and for the case of argument, let us say the larger value be the capital N. Say n1 is greater than n2, then this value cannot exceed n1 minus 1. So if this value cannot exceed n1 minus 1, then again also this condition holds true. This is larger than n1 minus 1. But what about the case if we consider n2? Now, since n2 is much less than n1, or should I say n2 is lesser than n1, so there is no chance this can be greater than, this part can be greater than n1 plus n2 minus 1. So I hope you understand why linear convolution doesn't work in case of DFT. And for that very reason, we must concentrate our attention towards the circular convolution. Now let us show how the circular convolution works by means of an example. So say if x of n is the signal 1, 1, 2, 2, 1 being the origin. Now as for the DFT signal, this origin signal symbol may or may not be given. So if it is given, then you can consider the arrow point being the origin, and if it is not given, then you can consider the first point to be the origin, which is always the case. And say h of n be 1, 2, 3, 4. Now the task is to find y of n, which is the circularly convolved signal x of n, and h of n, where both the signals are periodic and having a period n equal to 4, or both the signals having length of 4. Now let's go to the solution. Circular convolution almost occurs similar to that of the linear convolution, and in order to doing so, we must follow the following steps. First, we must mirror the signal, any one of them. We may mirror any one of the signal. Then we multiply the overlap part of both of the signal. Then we add all the values of the individual points, and finally we shift the signal by 1 point and repeat the process from multiplication and addition. So if we are to represent the signal x of n in the circular domain, then x of n looks something like this. If this is x of n, now in our case we are considering this to be the origin position, so this is x of 0, x of 1, the signal is progressing in the anti-clockwise direction. This is x of 2 and x of 3, and the consequent values will be 1, 1 over here, 2 over here, and 2 over here. Consequently, h of n will be, if this is our h of n, we divide the circle into 4 equidistant parts. This is h of 0, h of 1, h of 2, and h of 3. So h of 0 is 1, h of 1 is 2, h of 2 is 3, and h of 3 is 4. Now the first task is to mirror any one of the signal. So in our case we shall be mirroring h of n. So what will be the mirrored signal look like? If this is the circular domain, this will be h of minus n. Mirroring a signal simply means the time reversal operation. So if this was the previous value, 1 over here, 2 over here, 3 over here, and 4 over here, the previous direction was going in anti-clockwise direction. So by the virtue of mirroring, the new direction will be in the clockwise direction. So we shall start from the origin value. This will be 1. The next value 2 will come in the clockwise direction to this position 2. Consequently, this will be 3 and this will be 4. So in order to mirror a signal, if we place a mirror in this axis, then it is shown that these two places are mirrored, or rather exchanged with one another. Now, in order to multiply and add, let us go to the first step, where the new value here, h of 0, now this will be h of 1, h of 2, and h of 3. Remember, after mirroring we are going in this direction, so this is h of minus n, and the value consequently are h of 0 is 1, h of 1 is 2, this is 3, and this is 4. Now we are to overlap the signal with the x signal. So this is how we overlap. So this is our x of 0. Remember, x of 0 is still going in the anti-clockwise direction. X of 1, x of 2, x of 3. X of 0 being equal to 1, this also equal to 1, this is equal to 2, and this is equal to 2. Now what we are to do is just multiply this corresponding positions and add. So here 1 and 1 will be multiplied, consequently 1 and 4 will be multiplied, 2 and 3 will be multiplied, and 2 and 2 will be multiplied. So we get 1 times 1 is 1, 1 times 4 is 4, 3 times 2 is 6, and 2 2s are 4, which is equal to 15. This is the position of y of 0. Now we shall repeat this process for y of 1, 2, and 3. So now for y of 2, we are to shift n by one position. So let us do that. We shift h of n by one position. So the new signal is h of minus n plus 1. Divide it into equidistant parts. Now previously this position was our h of 0, this was h of 1, this was h of 2, and this was h of 3. The direction being in clockwise direction. Now we are to shift the signal by 1 unit, but in which direction? Now previously what I have shown that if we are to negate the value, we are changing the direction from anti-clockwise to clockwise. But since there is a plus before 1, we shall revert back to our anti-clockwise shifting. That means the signal will be shifted in the anti-clockwise direction. That means in mathematical terms, the signal will advance in the anti-clockwise direction, and we have considered the anti-clockwise direction to be our advancing direction. So the new position of x of 0 will be h of 0 over here. See, h of 0 has shifted in the anti-clockwise direction because we have done minus n plus 1. If we are to do minus n minus 1, then h of 0 would have come over here. So h of 0 is over here. This is h of 1, h of 2 and h of 3. Now, I'm sorry, there seems to be a mistake. We have shifted h of 0 over here, but still h of 0 is going in the anti-clockwise direction. Although the position of h of 0 has shifted in the anti-clockwise direction, but h of 0 will revolve in the clockwise direction, since there is a negative sign for h of n. So this will be h of 1, h of 2, and this will be h of 3. Okay, so let us put the value. H of 0 is equal to 1, h of 1 is equal to 2, h of 2 is equal to 3, and h of 3 is equal to 4. So our shifting operation is done. Now we must check for overlaps, multiply and add. So let us overlap the signal with x of n, where x of 0 is over here, which is equal to 1, x of 1 is equal to 1, x of 2 is equal to 1, 2, and x of 3 is equal to 2. Now let us see the multiplication. 2 will be multiplied with 3, 2 will be multiplied with 1, 1 will be multiplied with 1, and 4 will be multiplied with 2. So we get y of 1 equal to 2 times 1 is 2, 1 times 1 is 1, 2 times 4 is 8, and 3 times 2 is 3 2s are 6. So adding up this value, we get 17. So let us shift back 1 unit and repeat the same operation. Okay, now let us draw h of minus n plus 2. Now previously, in our previous case, this case, this was h of 0, this was h of 1, this was h of 2, and this was h of 3. 0, 1, 2, 3. The new position, h of 0, will be shifted back over here in the anti-clockwise direction. So this is h of 0. But h of 0 itself will go in the clockwise direction. So this makes h of 1 this point, h of 2 this point, and h of 3 this point. So plug in the value. H of 0 is equal to 1, h of 1 is equal to 2, h of 2 is equal to 3, and h of 3 is equal to 4. Now once again we overlap the signal and check. Now this is the overlap signal. Remember, we are doing nothing to x of n. X of n remains as it is throughout the operation. All we are operating on is h of n. So this is our x of 0, x of 1, x of 2, and x of 3. The values being 1, 1, 2, 2. Now let us multiply 1 will be multiplied with 3, 1 will be multiplied with 2, 1 will be multiplied with 2, and 4 will be multiplied with 2. So now this is our third operation. So we get y of 2 to be equal to 3 times 1 is 3, 2 ones are 2, 2 ones are 2, and 2 ones are 2. So this value equals, I'm sorry, there seems to be a mistake. This is 2, 4. 2 4s are 8. So adding this up, we get y of 2 to be equal to 15. Is it? 8 plus 2 is 10, 3 plus 2 is 5, 15. Okay. Now, once again, we are to shift. Fourth operation. So now this becomes h of minus n plus 3. Let us divide the circles. Our previous positions were, this is h of 0, this is h of 1, this was h of 2, and this was h of 3. So what we are going to do now is shift h of 0 in the anti-clockwise direction by 1 point. So this becomes our h of 0, and h of 0 will revolve in the clockwise direction, making this our new h of 1, this our h of 2, and this point our h of 3. Okay, now putting in the value, h of 0 equal to 1, h of 1 equal to 2, h of 2 equals 3, and h of 3 equals 4. Let us go for the overlap operation. Okay, very well. This is our x of 0, which is equal to 1, x of 1, which is equal to 1, h of 2, which is equal to 2, and h of 3, which is also equal to 2. Okay, now the repeating operation, 4 will be multiplied with 1, 1 will be multiplied with 2, 2 will be multiplied with 2, and 3 will be multiplied with 1. So y of 3 is equal to 4 ones are 4, 3 ones are 3, 2 twos are 4, and 2 ones are 2, which equals 13. 7, 11, 13. Okay. So now we'll stop our operation at this point, because if we are to shift h of 0 once again, h of 0 will return back to its previous state and the value will repeat itself. So we can conclude y of n to be equal to y of 0, which was 15, y of 1, 17, y of 2, it was 15, and y of 3, it was 13. So this is our resultant convolved signal. And as you can very well see, this is also within the range 0 to n minus 1, which is in our case 0 to 3. So this is also a signal having of length 4. So this is our convolution operation done. Now let us see a trick by which we can verify our result. This is merely a trick to verify the result in case of the exams. First, let us write x of n and its values 1, 1, 2, 2. Then we write h of n 1, 2, 3, 4. Now what we are going to do is multiply the first value of h of n with all the individual values of x of n. So 1 times 1 is 1, 1 times 1 is 1, 1 times 2 is 2, 1 times 2 is 2. We write it underneath the given values of x of n. We do the same with the second value of h of n. But before doing so, we shift by 1 unit. So 2 times 1 is 2. This will be written over here. 2 times 1 is 1. 2 times 2 is 4. And 2 2s are 4. Again we do it with 3 and shift. So 3 1s are 3. 3 1s are 3. 3 2s are 6. And 3 2s are 6. Same operation with 4. 4 1s are 4. We have shifted by 1 point. 4 1s are 4. 4 2s are 8. And 4 2s are 8. Now what we are going to do is add each of the column. So 8 will come down as it is. Now 8 plus 16, it is 14. So we are to write the whole value 14, not take 1 as carry to the next column. So this value should remain as it is. So 8 plus 6 is 14. 4 plus 6 plus 4 is also 14. 2 plus 4 is 6. Plus 3 is 9. Plus 4 is 13. 2 plus 1 is 3. Plus 3 is 6. 2 plus 1 is 3. And 1 goes down over here. So what we have essentially done, this is also a check for your linear convolution. If we are to convolve these two signals, this is the result of their linear convolution. But in case of circular convolution, what is the signal length? The signal length in our case is 4. So we take 1, 2, 3, 4. So keeping these samples, these 4 values unchanged, we take the remaining values and rearrange it under the first values. So 14 will come under the first value. Then 14 will come over here. And 8 will come over here. So now we are to add these columns. So 14 plus 1 is 15. 3 plus 14 is 17. 8 plus 6 is 15. And this value is 13. So this is our required result for circular convolution, which you can verify. So I hope you have understand the verification process. For this is both useful for the linear convolution that is used in section A and circular convolution that will be used in section B part of the questions. Now then, let us move on to the circular convolution property. So now we come to the circular convolution property. The property is quite similar to the convolution property of DFT, DTFT, CTFT, which says that if two signals are multiplied in the time domain, it will be convolved in the frequency domain, and the converse is also true. So if x1 of n is having a DFT of x1 of k, and x2 of n is having a DFT x2 of k, then as per the circular convolution property, x1 of n when convolved circularly with x2 of n, this will give us the value of x1 of k times x2 of k. Okay, now before going deep into the property, let us revert back to circular convolution. In the previous example, we have shown x1 of n to be 1, 1, 2, 2, and h of n, this is x of n, to be 1, 2, 3, 4, where both the signals are having a same length. But this is also true if they are having different lengths. Circular convolution can also be performed. In that case, if h of n, say it is 1, 2, what we need to do is we need to pad the signal with 0. That means in order to make the length same, we must consider two zeros at the end of the signal to make the length same. And padding 0 does not essentially change the value of the signal. All it does is help us perform the circular convolution. So that is something I forgot to say in the previous part. Okay, now let us move on to the convolution property. So if x1 of n and x2 of n are convolved, then the resultant DFT will be x1 of k times x2 of k. And this is also true if x1 of n is multiplied with x2 of n, then the DFT will be x1 of k convolved circularly with x2 of k, which we have shown time and again before. Now then, let us proceed to the proof. So as per the direct transform equation, we can write x1 of k to be equal to summation, where n goes from 0 to capital N minus 1, x1 of n e to the power minus j 2 pi kn over n, and x2 can be written as x2 of k, where summation n goes from 0 to n minus 1, x2 of n e to the power minus j twice pi kn over n. So now if we multiply these two DFTs together, we will get the resultant DFT x of 3. So let us write that. Say x3 of k is equal to x1 of k times x2 of k. And of course, the IDFT x3 will have a Fourier transform pair, that is x3 of n. This is IDFT operation. So let us operate assuming the IDFT operation from the definition of inverse discrete Fourier transform. We can write x sub 3 of n is equal to 1 over n summation, where k goes from 0 to n minus 1, x3 of k e to the power j twice pi kn over capital N. So let us plug in the value of x1 of x3 of k. So x3 of n will become 1 over n summation x1 of k times x2 of k e to the power j twice by kn over capital N, where k goes from 0 to n minus 1. Now we can put the value of x1 of k from the direct transform equation over here, and similarly for x2 of k we get 1 over n summation, where k will go from 0 to n minus 1, summation x1 of m e to the power minus j twice by km over n. So we are using a different variable m, since n already occurred in this transform, and we are to do so in order to get rid of any ambiguity. So the next value will be summation x2 of L e to the power minus j 2 pi kl over n, where the limit L goes from 0 to n minus 1, and here m goes from 0 to n minus 1. This is m, Mike. So the remaining part over here will come as it is, e to the power j twice by kn over capital N. Now what we should do is interchange the summation operators to serve our purpose, and it can be done so, as I have said time and before, as per the property of independent summation operator. So 1 over n remains as it is. We bring out x of m outside, I mean the not x of m, this summation outside, n minus 1, x1 of m, since it is dependent on the variable m, will go inside. Then summation L goes from 0 to n minus 1, x2 of L, and similarly k goes from 0 to n minus 1, will have e to the power j twice by k n minus m minus L over n, just simply multiplying these exponents. So I hope you understand this. So this part over here can be written in the form, can simply be written in the form of something like this: 1 over n